What if I told you there's a proof of the Pythagorean Theorem that came from a US president? Now, there are many proofs of the Pythagorean Theorem, but I always found this one to be pretty interesting because of both its simplicity and the fact that it came from, well, a politician. Garfield himself only served as the US president for a few months in 1881 before dying from an infection after being tragically shot. But in his time as a politician, he advocated for using statistics to inform government policy, and he had a strong math background. Now, as I mentioned, his proof of the Pythagorean theorem is surprisingly simple, depending only on some simple geometry. We start out with a right triangle having side lengths A, B, C. We want to consider another triangle that is congruent to this one, but in such a way that the base of the new triangle lies on the same line as the side corresponding to the height of our first triangle. We can do this by extending the side of length B by the length of A, like so. Next, we draw in the side of length B at a 90-degree angle, and since we have two sides and the angle between them matching the first triangle, the side angle side theorem tells us that the final side of the second triangle must also have length equal to C. From here, we connect the two sides of length C, and we want to figure out what the measurement of this angle theta is. Let's denote the angle between A and C by alpha, and the angle between B and C by beta in both of our congruent triangles. We know that the angles in a triangle sum to 180, and that each of our congruent triangles has a 90-degree angle, so we have the following, giving us that alpha and beta sum to 90. But since alpha, beta, and theta all lie on the same line, then their sum must also equal 180. After some simple algebra, we have that theta equals 90 degrees, and therefore this middle triangle is a right triangle with a base and height of length C. If we were asked to compute the area of this shape, one way to do it would be to decompose it into three separate triangles, like so. The area of each of these triangles is 1/2 base times height, so we compute the area of each and add them up to get the total area, which we'll call A1. This simplifies to give us that A1 is equal to AB plus 1/2 C squared. But that's not the only way to compute the area of this shape. In fact, if we declutter this image a bit, we can see that this shape is actually a trapezoid. We can use the area of a trapezoid directly, or simply decompose the trapezoid into a rectangle and a triangle in the following way. The area of the rectangle is A times A plus B, and the area of the triangle is 1/2 times B minus A times A plus B, giving us another way of computing the area, which we'll call A2. After some simplification, we get that A2 is equal to 1/2 B squared plus 1/2 A squared plus AB. Finally, A1 and A2 both represent the area of this shape, so we set them equal to each other. From here, we just subtract AB from both sides, and then multiply both sides by 2 to complete the proof.